Hello and welcome back. Today we'll be discussing how to interpret infrared spectra, specifically how different peaks determine which functional groups are present in a molecule. So first, a little background information. When a molecule is irradiated with infrared radiation, if the molecule absorbs that radiation, it becomes vibrationally excited, and that vibrational excitation must initiate a change in dipole for that molecule for us to be able to view a peak in the spectrum for IR. Okay, so energy, as we know, is inversely proportional to wavelength and directly proportional to frequency. Well, we don't use frequency or wavelength directly in IR. What we use is a unit called wave number, which is a little bit easier for us to deal with because we're not dealing with such huge numbers. Our spectrum is going to go from 0 to 4,000 wave numbers, and those units are given by inverse centimeters. So wave numbers are given by frequency divided by the speed of light, where our units end up in centimeters. Okay? So what we do is irradiate the sample with infrared radiation, record all of the absorbed frequencies, and those absorptions are characteristic for each functional group that's in the molecule. The intensity of the absorption is proportional to the change in dipole that's initiated by that absorption. So the simplest of our organic molecules is our alkanes. And we can observe the alkane functional group in IR. So you'll see here a simple IR spectrum, and again, our units are wave numbers, and so we see that the spectrum goes from 0 wave numbers to around 4,000 wave numbers. Okay? So the first thing we do to interpret an IR spectrum is notice that there's usually a peak just below 3,000. So we mentally draw a dividing line at 3,000 and look just below 3,000, and we'll see these peaks that are usually pretty strong. And that's because this peak is caused by sp3 hybridized carbon-hydrogen stretching, and there usually are a lot of these carbon-hydrogen bonds in the molecule, in an organic molecule, and that leads to this being a pretty intense peak. So this peak is due to sp3 CH stretching. And that's because this alkane here, which is pentane, has a lot of sp3 hybridized CH bonds. Okay, so another characteristic for an infrared spectrum is this region just below about 1200 to 1500. So let's just say 1500 and below. Okay, and that is called the fingerprint region. So a fingerprint region is characteristic for each individual molecule. If you have a library of compounds in your spectrometer, then you can run a sample against that library and determine which molecule you have, because this fingerprint region is characteristic for each molecule, even though it may have the same functional groups. For example, if we compared the fingerprint region of pentane with, say, butane, it would be very different because that's characteristic for each molecule, and that shows up at just below 1200 or 1500 depending on which molecule you have. So the next functional group that we're going to look at is an alkene. So alkenes are often similar in structure to alkanes because they often also have sp3 CH bonds. And so if you start with the dividing line at 3,000, just below 3,000 we have the sp3 CH stretch, okay? And just above 3,000 we have the CH stretch that results from the sp2 hybridized CH bonds. Okay, so those are some of the important features in this spectrum. Also, at about 1600, we'll have a bond that's characteristic for an asymmetric carbon-carbon bond. The carbon-carbon bond will have a change in dipole when it absorbs that frequency of energy if the carbon-carbon bond is asymmetrically substituted. So as in the case here, so 1-pentene has an asymmetric carbon-carbon bond because it's not symmetrically substituted on both sides. But if you had a molecule that was symmetrically substituted, for example this one, you wouldn't see a change in dipole for that peak at 1600. If you have a symmetrically substituted carbon-carbon bond, you lose this peak at 1600. And if you have a compound, of course, that doesn't have any sp2 hybridized CHs, for example, if you had a tetrasubstituted carbon-carbon double bond, then you would not see this peak just above 3000, which occurs at around 3100. So for an alkene, you normally have sp3 CH stretching just below 3000, sp2 CH stretching just above 3000 at around 3100, and the asymmetric carbon-carbon stretch at around 1600 wave numbers. The next molecule we'll look at is an alkyne. So alkynes also usually have the sp3 CH stretch just below 3000. And they have, if it's a terminal alkyne, an sp CH stretch at around 3300. And this is kind of a medium intensity peak. It's usually pretty sharp. They also have, if they're asymmetrically substituted, a weak peak for the carbon-carbon triple bond. And that occurs at around 2200 in the spectrum, or 2100. Okay, so those are the important peaks for an alkyne. And of course, here below, about 1500, we have the fingerprint region again. So the next molecule we'll discuss are aromatic compounds, and this one is monosubstituted. This is actually toluene. And so again, if we look at our dividing line at 3000, you can see that we have sp3 CH stretch just below 3000, and that's due to the sp3 carbon-hydrogen bonds here on this methyl group in toluene. Just above 3000, we have the sp2 hybridized CH stretch. And then we also have at 1600 a carbon-carbon double bond stretch. And another thing that's characteristic for an aromatic ring is what's called an aromatic ripple, which shows up at around 2100, 2000, just above 2000 there somewhere. So another thing that you can sometimes pick out on an aromatic compound are what are called out-of-plane bending peaks, which result from the hydrogens bending out of the plane of the molecule, out of the plane of the aromatic ring. Now you often can't see these because they are in the fingerprint region. If you have a monosubstituted benzene ring, those out-of-plane bending peaks are going to show up at about 750 and 690, which would put them right here in this spectrum. So you can sometimes determine your substitution pattern if you can clearly delineate these out-of-plane bending peaks. For example, the monosubstituted benzene ring shows up at 750 and 690. An orthodisubstituted benzene ring, or a 1,2 disubstituted benzene ring, such as orthoxylene, would have a single peak at 750. A 1,3 disubstituted or meta-disubstituted benzene ring would have 3 peaks at about 880, 750, and 690 for those out-of-plane bending peaks. And a para-disubstituted benzene ring would have a single peak at around 815. So here we have orthoxylene, which has all of the other features that we saw in toluene. We have that dividing line at 3000, a fingerprint region up to about 1200 or so, sp3 CH stretching just below 3000, sp2 CH stretching just above 3000, a carbon-carbon double bond peak, which is weak at around 1600s, probably right here, and an aromatic ripple at around 2000. Our out-of-plane bending peak is strong here at 750. For orthoxylene, metaxylene, or 1,3-dimethylbenzene, we have similar peaks. You can pick out the sp3 CH just below 3000, the sp2 CH just above 3000, the carbon-carbon double bond at around 1600, the aromatic ripple at about 2000, and the out-of-plane bending peaks at 750, 880, and 690. Here we have paraxylene, which has all of the other features, but then it has its out-of-plane bending peak at around 815. And again, these are in the fingerprint region, so they're very difficult to pick out. The next functional group that's important, and this one's going to be very important this semester, is an alcohol. Here we have ethanol, for example. We again have our dividing line at 3000, so just below 3000 we have the sp3 CH stretch, and of course this molecule has sp3 hybridized carbon-hydrogen bonds in it. Just above 3000 though, you'll see at around 3300 you'll see this broad peak, and this results from the OH functional group. This is from your alcohol functional group. This is called an OH stretch, and this is so broad because an alcohol functional group has hydrogen bonding, and this is going to broaden that peak because it increases the degrees of freedom available to that molecule. The only other thing that's really important in this molecule is that we have a fingerprint region just below about 1500. Our next functional group will be amines. So for a primary amine has one R group attached to it, and that gives it 2 hydrogens. So this is butanamine with 4 carbons and a nitrogen with 2 hydrogens on it. So again, just below 3000 we have our sp3 CH stretch. Above 3000, similar to an alcohol at around 3300, we have a broad peak, and again amines can hydrogen bond with other amines, and therefore they have a broad peak. But there are actually 2 stretching modes for a primary amine. There's a symmetric stretch where the hydrogens are going in the same direction, and an asymmetric stretch where they're going in opposite directions. Because there are 2 modes, there are 2 peaks in the spectrum if you have 2 hydrogens on that amine. So a primary amine will have 2 peaks. In the region that would be the same as an alcohol, around 3300. And again, we have our fingerprint region down here. A secondary amine, such as piperidine here, only has 1 hydrogen on it. And so because it only has 1 hydrogen, it can only vibrate in one way. So we only see 1 peak in that 3300 region for a secondary amine. Again, it has hydrogen bonding, so this peak is a little broader than you would expect for something that doesn't have hydrogen bonding. And just below 3000 we have our sp3 CH stretch. Okay, and the only other important region here is the fingerprint region, which is below 1500. It's important to note that a tertiary amine, such as, say, trimethylamine, would not give us a peak at 3300 in the IR because there's no nitrogen-hydrogen bond. Because that nitrogen-hydrogen bond is absent, tertiary amines are not interesting in IR. The next compound of interest would be a ketone. So this is methyl ethyl ketone. It has that carbon-oxygen functional group. So again, just below 3000, we have our sp3 CH stretch from all these sp3 hybridized carbon-hydrogen bonds. Okay, but the most important feature in this spectrum is the carbon-oxygen double bond peak, which shows up at around 1700. So this peak shows up characteristically around 1700 for carbonyls, and we'll often see at twice that number a smaller peak, which is due to the molecule or that functional group absorbing twice the radiation, and so or twice the frequency of radiation, and that is called an overtone. So at twice that frequency, or double the wave number, we'll get what's called an overtone for that peak. And so it can kind of look like you have an amine, but really if you have a carbonyl, seeing an overtone is very common. Another thing to note about carbonyls is that if you have a conjugated carbonyl, that will show up at a lower wave number. So if you have an unconjugated carbonyl, it's going to show up around 1700. If you have a conjugated system, though, remember we have resonance here, and so we could draw a resonance structure. In fact, we could actually draw 3 resonance structures here, but just to keep it kind of simple, I'm going to draw this one. And so because of resonance, that is going to lower the wave number where this functional group absorbs. So it may absorb at around 1680 or so. So if you have a conjugated carbonyl, it'll absorb at a lower wave number. Aldehydes have a characteristic absorption as well. And so this molecule, notice, has no sp3 CHs. And so if we look just below 3000, we don't see that sp3 CH stretch, but we see something else. We see these 2 little peaks here that look kind of like vampire fangs, and that's characteristic for the hydrogen on the aldehyde. So that hydrogen gives us these 2 little vampire fangs here at just below 3000, and sometimes they'll be a little obscured because of the sp3 CH stretch that often covers that same region. Again, we have a peak at around 1700 for our carbon-oxygen double bond. So I'm going to write aldehyde CH on here. We have a carbon-oxygen double bond at about 1700. We've got an overtone at around 3400. This is an aromatic species here, so we've got all the other features that were available for an aromatic system. I think I'm going to keep this simple by just sticking to the aldehyde functional group here. For an ester, we have similar features as a ketone, but we'll have something a little bit different, and that's a peak at around 1050 for that carbon-oxygen single bond here. In fact, it's really hard to pick out in this spectrum. It may be this one. Normally it's pretty strong, and you would be able to pick it out pretty easily, but right now this one is really kind of hard to pick out. We have our carbon-oxygen double bond at about 1700, And we've got our sp3 CH at just below 3000 and an overtone at around 3400. A carboxylic acid also has a carbonyl peak in it, so at around 1700 we're going to see that carbon-oxygen double bond peak, and those carbon-oxygen double bond peaks are usually very strong because when the carbon-oxygen double bond is vibrationally excited, that excitation initiates a strong change in dipole because there's a large difference in electronegativity between carbon and oxygen. It's very difficult to pick out the sp3 hybridized CHs right here because they're obscured by this huge broad peak here, and that's very characteristic for a carboxylic acid. So a carboxylic acid doesn't just form hydrogen bonds, it actually forms dimers, and those dimers lead to an even bigger broadening of that OH peak in the spectrum. So a carboxylic acid OH shows up between, even below 3000 up to around 3400 or above. Okay, so a very big broad peak there. And then the other features in the spectrum are really just the fingerprint region. Oh, we forgot our carbon-oxygen single bond that's possible, and in this case it's going to show up around 1050 as well. It's probably this one here, and again it's hard to pick out in this spectrum. So let's see if we can predict what our spectrum would look like for some of these molecules. Here we have a ketone, and this ketone has some sp3 hybridized carbon-hydrogen bonds. Okay, and so if we draw our IR spectrum, our wave numbers go from about 0 to about 4000. Okay, so at 3000, just below 3000, we've got some sp3 CH stretching. Okay, at 1700 we're going to have our carbon-oxygen double bond. Okay, and probably a small overtone at 3400. And everything else is pretty much due to the fingerprint region. Here we have an aromatic ring coupled with a ketone functionality. Okay, so our spectrum goes from about 0 to about 4000. We have a dividing line around 3000. Okay, and so just below 3000 we can expect a small peak for just the 3 sp3 CHs. Just above 3000 we're going to have some peaks for the sp2 CHs. Okay, we're going to have a peak at 1700 for the carbon-oxygen double bond, a peak at 1600 for the carbon-carbon double bond. Let me write 1600 down here. A peak at around 2100 for our aromatic ripple. Okay, and we have a mono-substituted benzene ring, which is going to have peaks, and now I have forgotten. Go back up and find that. Look at my little chart here. It's going to have peaks at 750 and 690. Okay, so we're going to have peaks at around 750 and 690 for the out-of-plane bending peaks because we have a mono-substituted benzene ring, and maybe a little overtone at around 3400. So that's most of the important features in our spectrum. Here we have an alkyne, and so this molecule, our spectrum goes from 0 to 4000. So at around 3000 we're going to have a lot of the sp3 CHs. We don't have any sp2CHs, but we will have a sharp peak for our sp hybridized CH right here. And everything else is going to be pretty much just fingerprint region for this molecule. Here we have a primary amine, and so if we consider our spectrum that goes from 0 to 4,000, we have our dividing line at 3,000. Just below 3,000, we've got our sp3 CHs, okay? And since we have a primary amine at around 3,300, we're going to have a broad double peak for both of the modes for those hydrogens. Those are the most important features for this spectrum. Okay, so I think we've covered the major functional groups that we wanted to cover the interpretation of for IR. And thank you for watching. Have a great day.